Pradeep. Okay, you'll have to rename yourself.
Oh, I didn't name myself that way. Sorry.
Well,
okay, I got it.
Confusion here.
I got it.
Can you please turn on your video?
Yeah, I would do that now.
Ah, great. Okay.
Okay, good.
Graham, you'd like to turn your, yeah, good, great.
Okay, super.
Yeah, nice to see you.
Nice to see you, Pradeep.
Yeah. I think we can go ahead. I think others don't know whether people are going to join.
All right then. Good evening and a warm welcome to everyone. Thank you for joining us today at the second webinar in the IRIS webinar series. The research initiative titled Molecular Materials and Functions is led by Professor T. Pradeep. It is my honor to introduce Professor Thalapal Pradeep, an institute professor at IIT Madras. He is the Deepak Parekh Institute Chair Professor and Professor of Chemistry at the Department of Chemistry. His research interests are in molecular and nanoscale materials, and he develops instrumentation for such studies. He is an author of over 100 scientific papers in journals and is an inventor of 125 patents or patent applications. He is a recipient of several awards, including the Shanti Swarup Bhatnagar Prize, B.M. Birla Science Prize, National Award for Nanoscience and Nanotechnology, India Nanotech Innovation Award, J.C. Bose National Fellowship, and National Water Award. He is the winner of the World Academy of Sciences Prize in Chemistry for the year 2018. The nation conferred Padma Shri on him in 2020. He is also the recipient of Nikkei Asia Prize 2020. We are also very fortunate to have a very distinguished panel from across the globe with us today. It'll take me hours if I get into introducing everyone in the panel here. So just a very warm thank you to all of you. Over to you, Professor Pradeep.
Thank you, Richu, for this nice introduction. I have just crossed 500 papers, just to make one correction. Well, let me thank my dear director for this wonderful initiative. Let me thank Karthik Raman and other organizing members of this series. Let me take a few minutes to introduce this distinguished panel, my collaborators joining from across the world. Some of them are not here because of various reasons, but most of them are here and you will hear some of them. I am here at IIT Madras. This is Professor Horst Hahn from Karlsruhe Institute of Technology. He is not joining us today. He is a distinguished professor of IIT Madras also. Professor Rob Wetton is from Northern Arizona University, Flagstaff, Arizona. He is not joining us today. Professor Sundar Gopal Ghosh is a professor at the Department of Chemistry at IIT Madras. Professor P.M. Ajayan is from Rice University, Texas, and he is also a distinguished professor at IIT Madras. Professor Piyush Ghosh is from Applied Mechanics Department of IIT Madras. Professor Graham Cooks is a distinguished professor at Purdue University and is also a distinguished professor at IIT Madras. Professor Rajneesh Kumar is from Chemical Engineering Department of IIT Madras. We also have Professor Tatsuya Tsukuda from University Tokyo. He is going to speak to us tonight. And we have Shobhana Narasimhan from JNC ASR Bangalore. Professor Umesh Wagmare, also from JNC ASR Bangalore, and he's going to speak to us today. Professor Manfred Kappes is from Karlsruhe Institute of Technology in Germany. He's going to speak to us today. He will soon be a distinguished professor at IIT Madras. Professor Thomas Bass is from the Institute of Inorganic Chemistry, Czech Academy of Sciences, Czech Republic. And Professor Robin Ras is from Aalto University, Finland. Professor Praveen Linga is joining from NUS Singapore. He is here with us today. Professor Hannu Hakkinen is an academy professor at the University of Jyväskylä in Finland. Professor Jianping Ji is from Singapore, National University of Singapore. He has also joined us today. In this brief presentation, I'm going to give you a feel of what we are planning to do. And this kind of a large, distinguished team is assembled because the problem that we are addressing is big. And obviously, such a topic cannot be covered in just a few minutes. So I would only give you a bird's eye view, glimpses into this. And molecular materials and functions, that is what we are talking about. It is such a broad thing and covers many aspects. So I will only be touching upon something. And our people are from all over the world. Of course, there are many more people, fantastic colleagues across other parts of the world as well, but they will join us in this initiative, not necessarily as participating investigators, but as visitors in the course of time. And that is the title, as you can see. And for me, this is a somewhat a basic science topic that we pursue, although we do applications-based science. What's happening across the world is that materials are becoming atomically precise, meaning with the increasing power to look at matter in greater detail with a large number of tools, one can probe larger and larger pieces of matter. This is one development. Experimental tools, computational tools, many others. Synthetically, it is possible to build matter with smaller and smaller pieces, constituent pieces. This one may call as nanoscience and nanotechnology. But then when you refer to that subject matter, the pieces with which nanoscale matter or nanomaterials is assembled need not be atomically precise. The moment you say atomically precise, you are talking about compositional control, structural control. Just as a molecule, a piece of matter can be built. And if you assemble such pieces of matter, you will create macroscopic pieces of matter. And this is happening in a very big way in many different materials today. Although I will be talking only about noble metals largely in this discussion, you have to imagine that periodic table is very big and one can extend this in all directions, not necessarily just with single element, but with compounds, many different directions this can be expanded. So therefore, we are talking about a continuum of materials that will come into in the course of time. And that, of course, is going to give you that broad set of materials would give very many new properties. Now, in this discussion, I will only take some tools, some techniques, most importantly, mass spectrometry. So you see that a small piece of matter or small molecular piece of gold that some years ago people discovered, here you are seeing the mass spectrum of that. It is gold 25 with some ligands, 18 of them, with one charge. And this is a piece that you can synthesize in a laboratory. And you can make milligrams. Today, we can make grams of this material. And this is the only material that you have in that bottle. What that means is that you can measure properties such as the molecular weight here or molecular mass in this particular slide. And that means that you can crystallize it. And when you crystallize it, obviously, you can create structures, or you can build structures, you can understand structures, you can computationally study many properties of these, such as the electronic energy levels. So this subject has expanded tremendously, and several people have contributed to this, and all these names that you see, and several of those people are here on this panel today. Now, a mass spec is a device wherein ions are passed through in some particular way. And you can use it to study many properties. For example, you can study a property such as chemical reactivity. So here is a cluster in solution, gold 25, let us say. And this kind of a cluster, or this is not necessarily gold 25, in this particular case, it is silver 29, it is also luminescent, meaning if you irradiate with ultraviolet light, you see some color, some other color that is coming. Then this is a solution of these molecules. These molecules can react. So some years ago, we asked this question, if you have this as a molecule and this as a molecule, can you have a chemical reaction between this? We showed that such reactions are possible. And not necessarily between just these, there are very many other molecules such as this and this. So you can do chemical reactions between these. So here is a molecule which is gold 25. Well, in this discussion, I am sort of disregarding the ligands. So here is silver 25. You mix these two together in the mass spectrum, you're supposed to see just this and this peak, but you see many other peaks in between. This is because of gold goes from gold 25 to silver 25, and silver from silver 25 goes to gold 25, although the M25 nuclearity is preserved. So how would this happen? This would happen by this cluster and this cluster coming together and forming some kind of an adduct. And you can see this adduct. This is that adduct with 2- charge state. You can characterize it. Computationally, you see that these clusters come together and interact. And when they interact, they form specific structures. And in that sort of transition state, you can see atoms moving. Very recently, we found that it is not that just this cluster, one cluster, another cluster interact, forming products through a dimer. It is also possible that many other dimers from the products, they also form and they also lead to several products. And this sort of very interesting chemical evolution can be studied, and that gives you kinetics. And this kinetics tells you that what is happening is very similar to a consecutive chemical reaction. A goes to B goes to C. This is something that A goes down and B goes up and decreases, C goes up. So this is something that classical physical chemistry, you would model it. And we can model all these chemical reactions happening in these. what it also tells you that if I have one cluster, another cluster, they are exchanging atoms. Within one cluster itself, atoms can be exchanged. And this is something that we saw by taking isotopically labeled clusters. So here is an isotopically labeled cluster. Here is another isotopically labeled cluster. This is pure isotopes, not just labeled. You have your pure isotopes of this gold, silver 25. This is another isotope of silver 25. This is all that is present. Of course, it is not 100% isotopic purity, 99.9 or 99.5% or so. So you have that, and you mix these two. So when you have this and you have this is what you had initially. You mix it together, you see that suddenly you get only this and these are completely lost. So you get isotopic mixing, and this is something that you can study in a time-dependent fashion, but it is so fast that initially just in 15 seconds, you measure one mass spectrum, in 20 seconds, at 25 and 30 seconds, this whole thing is gone. It means that the chemical exchange is very similar to something that happens between H2O and D2O. And such fast atom exchange, of course, poses a lot of questions to science. How would this happen with such atoms? We can study this with kinetics. I'm going to skip this. But it is not only that you can study these fundamental things. Using these clusters, such as these clusters, you can assemble them on plasmonic systems, such as a gold nanorod, and you can create such systems of this kind, which will combine plasmonic properties with the properties of individual clusters, as shown here with optical absorption spectroscopy. Gold nanorod and the cluster and the composite system is together. You can also image this in greater detail, reconstruct the structures. So when you have one cluster and another cluster, not only that these molecular crystals can be made A crystal and B crystal, you can combine these. So you can create such co-crystals, essentially giving you completely new properties. What would this give you? You can explore properties. In this particular case, these clusters, luminescence is explored to create new sensors. And these sensors can, of course, be incorporated into devices of this kind, which are water purifiers, and we work in that area. The other molecular system that in this center we will be interested in is gas hydrates. Gas hydrates are cages like these wherein molecules are trapped, and you can create interesting structures. They form at high pressures, generally high pressures, but you can also create them in laboratory atmosphere, as in ultra-high vacuum. So we have built an ultra-high vacuum instrument wherein you can deposit on a single crystal, you can deposit molecules of water layer by layer. And this is an instrument that we have built, which can be used to probe such materials using several tools, including infrared spectroscopy and mass spectrometry, secondary and mass spectrometry, and temperature programmed desorption and things like that. What we studied, or what we saw, was that in a chamber, in a vacuum chamber, you can simulate conditions similar to space. And in that condition, at 10 Kelvin and in ultra-high vacuum, you can create gas hydrates. And we publish that. So what that means is that this molecule inside these cages can possibly do interesting science. And this science, or this chemistry, this physics, can be probed with spectroscopy. And this is one of the motivations of the study. So this project or this center will have two phases. The phase one We will explore several problems, such as new methods to create nanoparticles of these kinds of cluster systems, their assemblies leading to crystals, creating new molecular materials with the method that Professor Graham Cooks will talk about, micro droplet synthesis, defect-free atomically precise materials and elucidation of their atomistic details with atom probe tomography and X-ray diffraction, co-crystals of different clusters leading to composite properties, high flux electrospray to produce cluster ion beams and spectroscopy. This is something that Professor Manfred Kappes will be interested in. New chemical reactions within the cages of clathrates and understanding elementary processes. This will be pursued along with Professor Rajneesh Kumar and Praveen Linga here. Detailed understanding of the properties through methods of computational material science will be of great excitement with Shobhana Narasimhan, Umesh Wagmare, and Anu Hakkinen. Umesh will be talking about some of these today. Pressure, electrical, magnetic, and many other stimuli can be used to create new environments, and we would like to explore properties of these materials. We have already started pursuing these with Piyush Ghosh, but then these have to be studied in greater detail. Phase 2, I do not wish to dwell on it in greater detail, but I touched upon atom exchange. Can you really trap these species in between when atoms are exchanging? Can you see them in real time? Can you model them? Can you see tunneling of atoms in these cluster systems? So many such interesting properties, and people say that some of these cluster systems can even be superconducting. And there can be exciting properties such as electroreduction and methanol formation and many others. All of these require new tools. For example, advanced mass spectrometry, with which we can study not just these small clusters at 10 kilodalton or 20 kilodalton. Maybe it is possible to study these clusters at megadalton. And you can probably conjugate them with viruses and several others and look at such conjugates in greater detail. I told you about atom exchange. That would mean that you study them under a microscope, such as this, a cryo-electron microscope. This particular thing has been supported by the center, but this is a support that is coming from Department of Science and Technology. All of these is so fascinating, and we are planning to explore them with all of our collaborators. I would now leave the stage for my dear colleague, collaborator Manfred Kappes. And let me take this slide out and then show his slide here.
So meanwhile, I can thank, first of all, everyone for listening to me for a few minutes. We're moving sort of in our thoughts 3.5 time zones to the west, to a place which is just south of Frankfurt, which you probably know, but parts you may not. It's 10 kilometers from the border to France, south of Frankfurt. It's 16 degrees Celsius, significantly colder at 2:15 in the afternoon, colder than I believe Chennai is at the moment. And what we do, which is perhaps of interest to this center, or one of the specialties, is that we work on ions in various contexts in a mass spectrometry kind of context overall. So here are some of the experiments that are available at KIT in my group, which we hope will be able to contribute to the center. We have a lot of home-built machines. So ranging from very cold temperature spectroscopy of ions, which we tag with helium, ions being molecular ions as big as the systems that you just saw in Pradeep's talk. We do on these ions also isomer resolved photoelectron and photodissociation spectroscopy, So sometimes the systems in gas phase have multiple frozen out conformers, so it becomes interesting to resolve them from each other because they have different spectroscopic properties. We're interested in time-resolved spectroscopy of the ions. We study that with femtosecond time-resolved photoelectron spectroscopy. And we have trapped ion experiments where we look at the photoluminescence of the species in gas phase without any matrix. And we also study their structures by electron diffraction if the structure is not already known from condensed phase. Common to Pradeep is a high-resolution ion mobility mass spectrometry, which we also do. And we collaborate, in fact, on the cluster-cluster reactions, which you heard about a little bit earlier. Eventually, the ions that we collaborate on, we hope to be able to put into condensed phase environment. We have an experiment where we study ions in neon matrix. So we soft land into neon, do spectroscopy in neon. And we have a what I call primitive mass spectrometry, which we have used in my group to study fullerene materials, for example, other isomers of C60, which one can separate and deposit, or we've been interested in connecting polyaromatic hydrocarbons. Now with my colleague here in Karlsruhe, Horst Hahn, who you heard about already in Pradeep's presentation, together with Pradeep, we hope to be able to make cluster-based materials by soft landing cluster ion beams. Soft landing means that energies that they don't fragment upon hitting the surface. And the corresponding machine is under construction at the moment here, helped in fact by someone from Pradeep's group, Papri Chakraborty, who is a very talented postdoc who we have recently gotten on board after another person who had been here already before, Ananya Bakshi, who also is a very talented person from Chennai. Thank you. This is all I have to say. I have 3 minutes, I think. I've used them up. Pradeep, we don't
Thank
hear
you, Manfred. And let me just now invite Professor Graham Cooks to make his presentation. But before that, I need to get his slides.
So Pradeep, while you do that, I'll just say a word or two. I'm very pleased to be part of the team and to be able to collaborate with you. Pradeep and I have worked together over many, many years. And this is an exciting new venture involving molecular materials. The part I want to talk about is making molecular materials, and the methodology I want to talk about is to use droplets. And so this is the key to what we want to do. We would like to take droplets, and in those droplets we will have 2 molecules. In general, those molecules will be forced. Here they are. Here are the little droplets that we create. The solvent will contain these materials in the droplets, and we will force them to react by the fact that the solvent is being evaporated. So you can take a couple of organic molecules. Here's one, here's another in the droplet's evaporating. The molecules are forced together, and you can do organic synthesis. This is an experiment that we've been doing for a few years. It's called desorption electrospray ionization. I'll call it DESI. And in the DESI experiment, originally, what we were doing was using the solvent itself to analyze materials. So this is a cover of Science some years back in which the droplets of solvent are impacting on the biological surface and creating, pulling off material, which are then analyzed. But if you deliberately look at a mixture of 2 species, we'll look at this on the next slide, you will be able to force reactions. So here we are in this little upper right. If we've got a mixture of 2 species, a yellow and a blue, we bring in our solvent, we create a secondary droplet. You saw those in the simulation, which contains yellow molecules and red molecules. They're forced to react, you get green molecules, and those green molecules can be then analyzed. So if we're going to do this experiment, this synthesis in droplet experiment in a comprehensive fashion, we can't do it one molecule and another molecule at a time. We've got to be able to do high throughput. And so the experiment that we're going to be doing, we're already doing, is a high throughput system in which we have a large number of samples. In fact, in the typical case, 3,000 or even 6,000 samples. Each of these samples is a mixture of two reagents. Those reagents are launched in the fashion that I showed above, and they give products which can be interrogated in the mass spectrum. So interrogating products tells you what's there, but that's not what we're trying to do. We're trying to actually make material using solvents, using micro droplets. And so this means that we not only need to be able to look at what's there, we need to be able to deposit that material, collect it, as well as analyze it. The next slide shows the full arrangement that we're using. A lot of these concepts, this high throughput concept, comes from biology and is slowly making its way into chemistry. And in particular, it's slowly making its way into synthetic chemistry, organic chemistry, which is what we're looking at here. So we take reagents in top left there of different types. We make an array of samples. That array, as I said, maybe 6144 different samples. And we transfer those samples onto a plate in the middle, a Teflon plate. And then we do the splashing experiment talking about. And we can go through at a rate of more than one reaction per second. The secondaries that come off can be analyzed, but they can also be collected. And so we're simultaneously collecting some of the droplets, and we're passing the rest of them through an iris and analyzing them. And so this allows us to collect material and then to proceed to characterize that material. So I'm showing you some fairly complicated apparatus here, but the underlying features of this concept are very, very simple. So the next slide shows an experiment that we did with Pradeep a few years ago. If you look at the A and the B on the right side of this experiment, basically all we're doing is we've got a solution. The solution has a metal salt in it. We're providing a potential HV, that high voltage, to create the droplets. Those droplets are then allowed to fall on a surface, which is at a different potential, and they both dry off, the solvent evaporates, and they're discharged. So the charged material in the droplet is discharged. And the net result after that is the growth of these very interesting metal clusters. They call the nanoparticles. So in sum, what I'm trying to do in this aspect of contributing to this project is to make molecular materials based on two facts that you've already now seen. One, in droplets, we can force organic molecules to react with each other. In droplets, we can create nanoparticles from metal salts. If we put those two things together, we should be able to force the reactions between metals and organics to create new types of materials. And in the last slide, this is in fact what I summarize. So this is our overall aim: droplet synthesis, organic molecules plus nanoparticles, making new materials. We have Coulombic force, we have desolvation, which represents an evaporative force. And something that is totally unexpected is we have very high electric fields at the surfaces of these droplets. Those electric fields are strong enough that if we take an ordinary organic acid, instead of the proton falling off of the acid, that's the definition of an acid, we will actually add a proton to the acid and create a new entity, which is then capable, as shown in the bottom here, is capable of doing new kinds of chemical reactions. So those chemical reactions, doesn't matter what they are. What we have in these droplets is high activity, high chemical activity, because of high fields, special reagents. I've already shown you we can do organic chemistry. I've already shown you we can do nanomaterials, nanoparticle deposition, putting both of those things together by mixing into our droplets organics, and metal salts, we expect to make a wide variety of entirely new types of materials. Thank you.
Thank you, Graham. We will we'll take questions. We will have questions at the end, and let me invite Professor Umesh Wagmare to speak next. And Umesh, let me.
Deep, shall I share my screen, or you will?
I will share your screen, Umesh, from here.
Okay, fine. Then I'll tell you to change the slide.
Yes, I will, but let me just get that slide. So Umesh is, as I mentioned, is joining us from Bangalore.
Thank you very much, Pradeep. It's my pleasure to be with you all, and I look forward to many interactions with the colleagues around. So I have quite a broad range of activities in my group. I have selected only some of the recent works which sort of connect with molecular materials in terms of their properties, functionality, and mechanical stability, each of which is an important factor for their applications, as well as some fundamental interesting ideas. So next, Pradeep. So first project is where I want to communicate to you. This is an example where we looked at properties of fairly complicated extended molecular materials, such as DNA molecule, and predicting its electrical conductance using molecular dynamics. But you know, it's impossible to do quantum mechanical calculations for fairly large molecules. So what we do in this approach is we pick a configuration from molecular dynamics, and the hopping or electron coupling between different base pairs, which is shown here in terms of a matrix here. Those coupling elements are modeled using artificial neural networks. Particularly, we use deep feed-forward neural network model. And then this can be used on the fly during molecular dynamics to predict electrical conductance of this fairly complex molecular system. Okay, so I will be happy to bring in the artificial intelligence or machine learning ideas into modeling some of these materials we have. Next, Pradeep. Yeah, thank you. So here I'm showing you an example where we worked on two-dimensional materials and how to modify it at atomic scale. Like Pradeep mentioned, it should be possible to have atomic scale precision in these systems. And here we are predicting a specific catalyst based on MOS2 by engineering substitutional gold and sulfur vacancies. And this is for direct synthesis of hydrogen peroxide, which is quite an important reaction, which can make a fairly important impact in different sectors in industries. So what we showed in this is we started with lots of configurations of MOS2 with golden vacancies of sulfur, and then use screening based on adsorption of certain intermediates, specifically oxygen molecule and proton on these surfaces, and then selected only a few of them, which we found that if you have a combination of substitutional gold and sulfur vacancy, they promote the reaction limiting step, the rate limiting step, the barrier goes down. In fact, this is without sulfur vacancies, and this is with sulfur vacancies on the right. And you can see the barrier comes down and the reaction becomes absolutely smooth. So it's a sort of totally computational prediction of a new catalyst for DSHP. Next, Pradeep. So next is an example of a type of molecular material called metal organic framework. These are, of course, very interesting, rich class of materials, but many people worry about their stability, mechanical as well as over long term. So they often fail through amorphization. So we here took a very simple example of a classic MOF called MOF5, and it is known to amorphize at extremely small pressures, relatively, okay? Like 40 megapascal, the material amorphizes. So we have used here computer simulations based on first principles density functional theory to show that, as seen in the first picture here on the left, there are torsional modes of various molecular moieties which make this material, which become unstable at very tiny pressures. And you know, this is the phonon dispersion of the starting MOF at 0 pressure. And this is at a very tiny strain. You will see that these are the phonons at the bottom, which are unstable. These circles, color circles, blue and magenta were stable in the reference structure, but they become unstable at very tiny strains. And that lead to a structural transition, which subsequently lead to combination of shear strain and local distortion. And it involves no bond breaking, that all local coordination of various moieties is preserved, and yet you get very huge reduction in porosity and amorphization. So this is an example of a work which can be useful in understanding mechanical stability of molecular materials, which I feel is very important, particularly when many of them are likely to be metastable and synthetically made. Next, Pradeep. So the last question we addressed is flexibility of molecules, particularly molecular solids, which will be very important. And flexibility is a term which a lot of people use in material science in different contexts, but very loosely. There is no single quantitative measure available for flexibility of solids. And in this work, which is yet to be published, we have proposed a new measure of flexibility, which borrows from the flowability of a liquid and basically addresses how the flexibility of a solid is inherited from the flowability of a liquid. So here I'm showing in the second row of this figure, basically, if there is no internal degree of freedom in a crystal structure, the crystal cannot be flexible. Whereas if you have internal degrees of freedom, which preserve the symmetry of the lattice, you can have greater flexibility. And on the right-hand side is a figure where we show different classes of crystals, starting from hard zinc oxide. Here is the bottom. You will see the flexibility is very low. And then the negative thermal expansion material, zirconium tungstate, which is intermediate, and then MOF5, which I described on the last slide, then ZIF8, which is the highest flexibility. So this measure is quite successful. I'm not going into details of it, but the insights it gives are very interesting. Earlier, people used to believe that high flexibility is associated with small elastic modulus, like a soft material or a molecular material. What we show is, well, softness is important in accommodating large structural adjustments at low energy cost, but also hard phonons are very crucial in absorbing the elastic energy and retaining the structure. So this is the new insight we have obtained from this analysis. Next, Pradeep. This should be my last slide, and I tell you a few other topics we work on, which may be of relevance sooner or later to the topics proposed in our project. We have fairly strong work activity in the areas of ferroelectrics and thermoelectrics, and more recently phase change materials, particularly metavalently bonded crystals and hybrid perovskites. They are also linked with electronic topology. More recently, we are working on high entropy alloys, of course, 2D materials with a twist. And finally, we are also using machine learning extensively to learn from relatively small data sets, which are common in material science. And thank you, and I look forward to lots of interactions with you all. Thanks, Pradeep. I'm done.
Thank you, Umesh. Our last presentation today is by Tatsuya Tsukuda from Tokyo. So he's, let me take that presentation.
Thank you very much, Professor Pradeep, for giving me this opportunity.
Yes.
I will be talking about, okay.
Yes.
Okay, so I will be talking about our research activities in the next 4 minutes. I'm from Tokyo. My name is Tatsuya Tsukuda. Okay, please, next. So our research target is very small metal clusters composed of less than 100 atoms. And we call these small clusters as superatom because of the similarity in the electronic structures with the conventional atoms. So by surface protection with the ligands, we can treat these superatoms as a conventional chemical compound. And we treat these chemical modified superatoms as an artificial element at the nanoscale. So and we have 3 projects on this type of targets. Next, please. The first target is, our first project is the development of new synthetic method of the new superatoms in high yield. We recently found that the hydride doping, H- doping to some superatoms can induce a variety of chemical transformations, such as core growth and the radioselective doping of other elements, and the surface modification with the different ligands. And we recently found that the two superatoms can fuse into a dimer of superatoms by this approach. Next, please. And the second project we are working on is the exploration of the new properties of superatoms. We are interested in photoluminescence of superatoms. As you can see on the left, gold-13 clusters protected by Cal beams are very stable and exhibit photoluminescence with high quantum yield with a 60%. And very recently, one of my PhD students discovered that the iridium doping at the central position of the icosahedral gold superatoms can enhance the photoluminescence quantum yield up to 70%. So this is very bright superatoms. Next, please. So we are also interested in the catalysis of superatoms. And we recently successfully synthesized a new gold superatoms, gold-24, in PVP, polymer matrix. High-resolution TEM image show that the structures are fluctuating all the time. And with the help of DFT theoretical calculations, we realized that all atoms are located on the surface of this superatom. And they show very high activity for aerobic oxidation of alcohols in water. And we also use ligand-protected superatoms as starting materials of the heterogeneous or supported catalyst. Next, please. And the last project we are working on is the development of the new characterization method of the chemically synthesized superatoms in gas phase. So here is one example. This is an photoelectron spectrometer developed in our group. Now we can introduce chemically synthesized clusters in solution into vacuum via ESI source. And after mass selection, we shine the clusters with the laser light to detach electron from the clusters, superatoms. And by measuring the electron kinetic energy of the photodetached electron, we can recall the photoelectron spectrum of the size-selected superatoms. Next, please. And by using this method, we can probe the intrinsic electronic structures of the superatoms without the absence of the solvents and the counter anion. And the left panel shows that the electron affinity of silver superatoms can be reduced dramatically by doping a single palladium or platinum atom at the center. On the right, multiply charged silver superatoms do not electron in the gas phase, although the electron affinity is negative. And this is due to the electron is confined in the superatomic core by the repulsive Coulomb barrier created by a negatively charged surface unit. Next, please. And this is the last slide, and this is my dream. I would like to create a periodic table by using superatoms as a function of the number of electrons confined in the superatoms. And then by using these superatoms as a building unit, I would like to create quasi-molecules or assemblies of superatoms like this to explore new functionalities. Thank you very much for your attention.
Thank you, Tatsuya, for that nice presentation. We are done with this set of presentations now, and maybe Karthik Raman can take it forward.
Hi, am I audible?
Yes, you are.
Yes, hi. Thank you, everyone. We thoroughly enjoyed your very detailed presentation. We're very grateful that all of you could join us here today. So we'll formally end the webinar now, but if there are a lot of questions that has come. So if Professor Pradeep would like to take on the questions, we can do that. And the conversations can continue.
Well, there are questions and there are 292 people here. So let me take all the questions if it is possible, as many as possible. But then in case I miss something, please excuse me, okay? So let me, probably some of these questions may be repeating. So therefore, I will go from the bottom and go up. Okay, so please share all. PPT will be shared. We have to attend certificate. Thank you very much for excellent. Kindly submit the questions. Lud Xavier asked a question to Professor Kappas, I suppose, regarding electron diffraction source. What is the time resolution? Is it possible to study femto attosecond excited states? How many electrons per pulse? You can see all these, Manfred, on the right side. Please, and can you please answer this?
Yeah, so it's 40 kilovolt electron beam, 10 to the 5 mass selected cluster ions, which are, it takes about 3 hours to do an exposure for a specific temperature. Yeah, so you cannot do femtosecond time resolved. You can only get, as a function of temperature, you get the structure if you do modeling to fit the diffraction data. Okay.
Very nice. How many electrons per pulse, bunch, etc., if it is a pulsed source?
That's about a microampere current electron beam. Yeah, so it's not pulsed.
Gaurav is asking a question. What will be the impact of clathrate hydrates formation in UHV? How it will impact the chemistry and physics of star formation? Can Rajneesh take this question?
Yeah, why not? Forming hydrate at low pressure, there is a lot of challenge in terms of kinetics of hydrate formation. Since at low pressure and low temperature, you don't expect these molecules to really come together that well. So there are a lot of kinetics challenges, and this is what we try to basically sorry about that. So basically because of low pressure and low temperature, you will have these kinetic issues, and to basically go somehow manage these kinetic issues, you will have to have better mass transfer and heat transfer properties on these hydrates. So we do all that aspect. We study these in our lab and try to improve the kinetics of hydrate growth.
I don't see other questions. Others are largely to greet people, etc. So in case you have other questions, please, we will wait for a few more minutes. Yes, Pallab is asking a question here. Atoms are moving from one cluster to another, and you can force chemical reactions also. Is it possible to assemble atoms of our choice, that is an Ag atom in AU cluster, that too with specific location? Tatsuya, can you take this question?
So yeah, thank you. Atoms are moving from one. So what I saw is the structure isomerization within one cluster. So I didn't study atom diffusion between clusters. Okay, so the second question is, so yeah,
but
element can be doped.
I mean, it all depends on the stability of a given cluster that is formed.
Yeah.
Which specific location of a cluster will depend on that.
Yeah, elements prefer has some specific preferential site for the doping. So platinum palladium dope can be doped at the center, and silver can be doped at the surface. So element has some specific site for the doping.
Lourdes is asking a question to Umesh Wagmare. Umesh, can you take this? Could you comment on impact of machine learning on new materials discovery and design? What is the state of the art currently in the world and in India? What is in store?
Yeah. So thanks, Pradeep. I will respond to this question and also a few others that I located in Q&A. So first of all, as of now, there is no real material which is out as a product which has been predicted using machine learning. Although there has been a lot of efforts for the last 20 years in this area, particularly initiated in the United States. There are many databases available now. Some of them are also generated from within India. They're ranging from metal organic frameworks to 2D materials to clusters to intermetallics and quantum materials and so on. And these databases are all available on the internet. One can use them with your choice of machine learning tool of analysis and learn from them. So, but as far as the next phase is concerned, what is required is actually to combine experimental and theoretical data. You know, one can't rely on the data alone from theory, and there is a lot of need, and now efforts are in the direction to combine source data from experiments as well as computations in sort of learning and predicting new materials. Someone asked about the graph convolution on neural networks. Yes, these are quite useful. These are used for modeling interatomic interaction potential, something which DFT gives you, can also be modeled using machine learning. So machine learning can be used in prediction of properties. It can be used in modeling interactions between different atoms or clusters in the present context. There is a huge scope. It's a kind of a unifying framework which doesn't care about where the data comes from, what type of data it is, but it's possible to learn and identify patterns in them.
Thank you, Umesh. I was just looking at the chat and the number of questions there. In the Q&A, there are several questions as well. Some of them Umesh addressed. I'm going from the bottom here. If some of you are seeing this, would there be applications of superatoms in explosive formulations? That's a question. There are several explosives that have come just because of the nanoscale dimension. Some of them are already commercial in several areas, aluminum and magnesium, for example. But then there are boron-based cluster systems that are coming up, and this area is active. And can we stop sound by transparent material instead of any solid material? Similarly, any transparent material that can be created to control wave property energies like sound, light. Well, I do not have an immediate answer. Can you stop sound by nanoparticle materials, Umesh? Is it?
Can I respond, Pradeep? Yeah, sure.
Please.
So, see, although the question asked is in the context of sound propagation in a crystal, this is actually the holy grail in the field of thermoelectrics. If you want a high performance thermoelectric, you want a material which will be very slow in propagation of sound waves. Yeah, the reason is most of the heat is conducted by sound waves in a crystal. Yeah, so there is a huge effort in designing materials in terms of nanostructuring or even clathrates that Pradeep mentioned about, and other types of materials like zinc solids, where there are different ways of slowing down the propagation of sound waves in the material. If I have to answer your question in a very simple way, well, if you create little vacuum inside your material, that will slow down, that will stop the propagation of sound wave. Yeah?
Fantastic.
So molecular materials are great. If you create void spaces in between them, they will be very slow in propagating sound waves.
Very nice.
And all of them are transparent because none of them is metallic typically, particularly metal organic type systems. Thank you.
Thank you, very nice. And there are other comments like principle of transmission electron microscopy and all that, which we will not take up right now. There are ways of getting that information. Is it possible to synthesize clusters and mixed nano oxides? Yes, there are many clusters of oxides, sulfides, chalcogenides. So these are all coming up. And as I said in the second slide or so, in periodic table, if you expand, there are many different directions that you can look at. And as the last slide of Professor Tatsuya Tsukuda was talking about, his dream is to create a periodic table with varying number of super atoms building the periodic table. So that's the way it is, and it need not necessarily be viewed from the point of view of just elements. They can be oxides and many others. What's the stability? Of course, there are very many superatom materials today stable even up to 350 degrees centigrade. So this is very much possible. And there are other stabilities also, not necessarily thermal stabilities alone. Okay, can we replace the experiments? You did address this, Umesh, already with artificial neural network.
That's right. The idea is not to replace, but to combine.
Correct. And graph theory also, you looked at that, and classical method selection of learning rate. Okay, I suppose we have addressed all of them, I suppose. Why AU nanorod is having dark bright portions in the TEM? This was a composite gold nanorod system, and the nanorod by itself is dark, and the lighter regions are cluster materials where the electron density is lower. So that is why the differential contrast is appearing. So I have we have addressed all the questions. In case you have additional questions, please do write to us individually. There is one last question here just came. Are ligands having any role to play during atom diffusion from one cluster to the other? Yes, indeed. There are ligands are very important in this, and we have studied this in great detail. This subject area is being looked at by several others as well. Richu, we are done with this.
All right, then we can wrap up. Thanks to everybody who's joined us here today. We thank you for your time and for
I would like Richu, before we close, I would like all the panelists to switch on their videos and then take a picture with all of them.
That's a wonderful
already
idea.
Recorded. Yeah. Suraj, Rajneesh, Ankit, all of you. Thank you very much. Thank you very much.
Okay,
nice,
thanks.
Seeing you all.
Thank you, everyone. Thank you.
Thank you.
Thank you all. Thank you, everyone. Thank you, Professor Pradeep.
Yeah.
Thank you, Jianping. Thank you,
Thank
Praveen.
you.
Yeah.
Thank you, Richu.
Thank you. Thank you,
Bye-bye.
Professor Rajneesh. Bye. Bye.
Take care. Bye.
Thank you, Professor Pradeep.
Well, yeah, very nice. Dr. Karthik, was it okay?
I think it was great. Yeah, just, the number of questions and the number of people hanging by at the end tells the story. So thank you so much.
Yeah. It was somewhat too technical, but I mean, it didn't overshoot, but all right.
I think it really covered the breadth of the work and, the possibilities. I think people must have learned a lot from this. Eventually, the students should have really taken back a lot. So, yeah, thank you. Thank you so much.
You asked me some contacts. I had given that already. I don't know whether.
Yeah, I think it was very widely circulated, and just shows in the number of attendees we had today.
No, not about this, but some other reason that my contacts.
Okay.
in the context of global engagement.
Right. Yeah. Yeah, so that's going on actually. So we'll keep you posted on that.
Okay. So this will be eventually edited and then posted, right?
Yeah, so we will share it with you. You can give your comments. So would you like anything to be edited out in particular?
Oh, nothing. These are all fine.
Yeah. So it's already, it was streamed live, but we can mark it as, so if one of the PAs requests, we could mark it off as private, unlisted temporarily, to make some edits, but it was already streamed live and it is available on YouTube. So I'm sure there are people watching it right now who tuned in late. They're probably catching it on YouTube right now and so on.
Correct. So you can cut off the end and a little bit in the beginning and a little bit at the end, so that
including, I think we should stop the recording now. So
and
yeah. So this part.